Importance of monitoring, just to mention, if you go on the homepage of the Austrian Society for Geomechanics, you could download a handbook for monitoring, which is written in English language, which gives a very good overview of what is possible and how can we come to the result. It's for free, of course. And yeah, I bring a little bit the input of this. The principle is the ground reactions taking the form of lining deformations. Yeah, we get lining deformations and lining pressures are measured, and the stability of the excavation is confirmed by frequent monitoring. I like to compare it with a medical doctor. I mean, if everybody of us would be one single person and everybody of us is the same, then we just would need one doctor and he always would give the same receipt. But what do? We go to the doctor, he measures the fever, he measures the heart frequency or whatever he measures, what he thinks is a good thing to measure, but then he doesn't stop. What does he do? He goes to an evaluation of his results, combines all these results. I like to say he makes an interpretation, and from his interpretation he gives you the right medicine. Nobody knows if he is right, and if it is the right medicine. That's why you take it. Nobody would expect that in the next second you were, let's say, sick, and in the next second you are healthy. Nobody would expect that. Same in our geology. So we take this medicine for a while, let's say for a week, then we go to the doctor back and ask, yes, these were the results, should I change my medicine, yes or no? Or maybe I don't even need one. And I like to compare the situation because it is completely the same than we do in underground engineering. Our patient is the rock, and it was in equilibrium when we did nothing, so it was really healthy when we were not there. But then we came and made an underground structure. And we, as you saw on my first slide from today, we brought the whole system into not being in equilibrium, and our big goal is to bring it back to equilibrium by using the right medicine. So, comparing that to what the doctor does, we have to measure something of our rock. And I like to talk, I mean, talk is maybe I have to go to the psychologist, but to talk to the rock and say, okay, I give you 10 bolts, is it okay? And I see it when I measure your stresses in your bolts. And if the stresses in the bolts is not too high, 10 was maybe too much, I can reduce it a little bit. But I have to measure my stresses in the bolts, otherwise I don't know if it's okay or not. Now, why do we need that monitoring? Yeah, it's like, as I mentioned before, everybody of us is different, the rock is different. And we in the design stage must be clear. We make a lot of mistakes. Limits in the accuracy of the geological model. I mean, the geologist does what he can, but he cannot look into before we are there. Lack of rock and rock mass parameters. I mean, the geologist selects a sample from here, and from there, puts it in the laboratory, and we do some sampling. We get a feeling, or is it hard rock, soft soil, what is it? But a lot of parameters are missing, this must be clear. We have a limited knowledge of the in situ stress. I mean, we always say gamma times H is the stress primary when we start. And what about if we have a slope? The tunnel is here and we have a slope. Do we then calculate this height for the primary stress there? Or is an influence of the slope here? I mean, this we could solve with numerics. But if I don't do that, I have a very much limited knowledge of the in situ stress, which is the basis for all the design steps afterwards. Uncertainties and simplifications in the mathematical model. I showed you the easiest material model which we use in geomechanics, which is called Moore-Coulomb. Yeah, this is just one out of I don't know how much. If you would like to use Moore-Coulomb in London clay, the British guys would throw you out, yeah, because there is a Camp Clay model, hardening soil, and all these things. The good thing is the material models are perfect, but you need 20 parameters and nobody knows. You can determine 5 of them, and the rest of the 15 is expert knowledge. I don't know how you act here in Argentina. You have your own material models, and nobody knows the parameters because in this Camp Clay model there is no test specified how to come to these parameters. So you need the expert knowledge of those who wrote the material model because only they know the 15 parameters, just 5 can be determined. I'm not a fan of that. We must be clear that there are simplifications done. A more Coulomb, everything can be determined because it's such an easy material model. But it is not the reality. This must be clear. Yeah, another reason why we would like to make monitoring. Verify the applied rock classification. We have to watch. We had a design on this. And what do we really meet in reality? Somebody has to monitor. We have to control the tunnel stability. That was the reason why I brought this lesson into here, because we saw there are some cases where we have instability and we will have to avoid that. Another point is we would like to optimize the support. I mean, if the problem what we face here is we nowadays measure the utilization of the shotgrid. So to say, do we have too much or too less shotgrid in? The colleagues who are responsible for that react immediately if we have too less shotgrid. So if we have a utilization of 95%, they cry and say, no, please make more shotgrid. The funny thing is, and this is again psychology, if we have 20% of utilization, you will never find a guy who comes to your office and says, we have too much shotgrid, please reduce. Yeah? Nobody says. It's a funny thing. Maybe it's too new, but if I have 20%, I could come in the office and say, let's reduce. But the psychology says, okay, they said 20 centimeters we keep. Yeah. So to optimize the construction sequence, I mean, we can build by sidewall galleries, top heading, however we would like to do that. Optimization is possible. If we think on a design, it is clear that we have parameters found, and these parameters have a certain range. You get back from the laboratory a certain range of these parameters. When the range is not too wide, your safety, you will put, as a designer, you will put a safety factor on it. And when the range is very wide, your safety factor will be a little bit higher. This is also clear. I don't know how the situation here in Argentina really is. In Europe, tunneling is the only field which has no Eurocode. We have Eurocodes for everything nowadays. And we are very happy not to have a Eurocode, and we will fight for that, because the Eurocodes, they give you fixed safety parameters, don't care on anything. Yeah. So, for example, I have, let's say, a very high knowledge. No, they put safety factors on the load, they put safety factors on the parameter. At the end, as I told before, we get a thickness of 65 centimeters, where the same colleagues would have built this tunnel maybe with 30 centimeters some years before. I don't know why this is going into this area. Everybody wants to have, let's say, no responsibility. I follow the Eurocode and that's it. Yeah? And then I'm safe, and if we have a collapse, somebody must be, but not I am. Yeah? So anybody takes the responsibility, I follow. I just wanted to say we are free to choose the safety factors for the moment, and it must be clear that there are zones where we don't have so good parameters available. For example, the Brenner base tunnel has an area with these 1,800 to 2,000 meters of overburden where we don't have any sample. Yeah, we will build the tunnel there. But it is clear that we are missing an information. We have a model transferred from a tunnel which is, let's say, 200 kilometers in Salzburg, which is 200 kilometers away. But the geologists explain there is a geology in Austria which is looking like that one, and it will be more or less the same then in Tyrol. So we are working with this information further. Why do we need now this geotechnical stuff on site? Coming from the design, we expect to have, we call it a normal behavior. So the design tells us, I will expect 5 centimeters of deformation, for example. And as long as I get this normal behavior and the geologist tells me, yes, it is this geology which you had in the prognosis, I'm fine. But what happens if these parameters turn away from the normal behavior? Then there must be somebody who sees that. And what we learned is the construction site manager cannot. He has to do so many things. Organization of the construction site, meetings nowadays. This is really a problem. And he cannot focus too much on statics and then on geotechnical issues. So there must be someone. And if it's a good geologist, he sees, okay, we are too far away from the normal behavior. Geologist, please come explain what is the change. And then it's a decision process. What we learned is there is no one on the construction site, because nowadays there are so many people sitting in the construction offices, in the meetings, I mean. And everybody, I tell it very free, everybody is more clever than the other. So it is no way that one says, I have the idea and we do it this way. No, it takes a decision process. It takes a long time to make the decision, because the one has to check, he suggested some pipe roofs. Do I have pipe roofs in my contract? If yes, and the price is not good, I will not agree. If I don't have it in the contract, I can make maybe a claim out of it. And this is the play we have to, this is the game we have to play. A decision process which takes time. Yeah, but the rock is not waiting for us. Yeah? The rock doesn't say, okay, make your decision. I do not deform in this time period, so I will wait for your decision. The rock deforms. It is the analyzing process of the medical doctor. I'm already having, let's say, a fever of 39 degrees. My fever doesn't wait until the doctor is ready. No, it goes ahead. Then, hopefully, a decision was made. And we say, okay, we will put in this and that material. Okay, maybe we have to organize this material. It's not placed on the construction site, so this again needs time. Then we put it into the rock, and the rock will not immediately be back again to the normal behavior, fall down here. No, same situation then I said before. We take the medicine for a week, and then we'll see what happens. So the rock comes back to the normal behavior if we did the right measure. After a while. If we have a little bit a lazy guy on the construction site, he didn't see that, or we have no one, just anybody sees, oh, we have already a crack, the decision process will take almost the same time, even if it's already a little bit too late. The decision process will take its time, the action will take its time, and hopefully we come back to the normal behavior. But in some cases, we are there. And then this is just to show you why we installed a geotechnical group, geotechnical engineer, geologist, in very good contact with the designer. The geotechnical engineer has to come from the designer. This is, in our opinion, a must, because nobody knows better what he calculated. So the one who calculated should then be the one who checks if everything runs right. The main difference to the geologist, who should not be the one who did the prognosis. Yeah, now I'm back at these green colors. We are in the opinion, we do it now regularly on every construction site, that we say, this is, let's say, the normal behavior. If we are in between, we call it, in a certain range, we call it warning level 0. If we are outside of that, we call it warning level 1. And if we are over that, warning level 2. So what does it mean? 0 means we have a system behavior. I mean, the tunnel behaves as we, let's say, expected within a range of a target behavior according to the specifications. We say normal behavior. 1 means a deviation from the expected system. A reaction phase has to be started. So we have to call the construction site manager, we have to call the client site supervision and say we have to sit together, something is not going in that way we want it. Then in red 2A means imminent danger. But this is a danger which only reflects to the construction site, so no public is concerned out of that. And B would mean here we also affect third parties. And you might have heard of our big collapse, Lassing, where a house was collapsed. And people in were dead and 9 miners also were dead. So from this point on, everything changed. And also the manager said, no way, we follow safety first. What should be done in the monitoring? First, we should think on what are the parameters we would like to know. The prediction of the magnitude we await. The selection of the instrumentation and its accuracy. What is the accuracy we need? Then, where do we put the location? Where do we locate this instrument? Then, who is and how do we collect the data? Who is doing the data processing? And then we need an interpretation. The most important thing on the medical doctor is the right interpretation. This is a good doctor or a bad doctor, because the analysis can also be done by a nurse in many steps. But the interpretation, this is the good or the not so good doctor, and then a report plan to that. What can we measure? Deformations, of course, stresses, forces. Here I come back to the question of the groundwater, piezometric levels, meaning groundwater levels, temperatures. Typical main cross-section. Why do I say main cross-section? I mean, in the design, the designer has to say, okay, this tunnel is, in our case, this Brenner base is 60 kilometers long. I cannot make thousands of calculations there. So I have to choose where are my critical sections. There I will do a design. And the main cross-section for all these measurements should be placed there where I did these design cross-sections. Typically we have these mirrors where we measure the deformation of the shell. We put in some measurement units into the shotcrete shell to measure the deformation and the stresses in the shell. And we put in some extensometers, as we call it, multiple extensometers, to see what is going on outside in the rock. And we would like to compare what is going on in the rock and what is going on in our shell. Typically, we install these mirrors in this shotcrete shell, as you see. So it is telling us what is the movement of the shotcrete shell. This is the target. As the miners do not take care on measurement units normally, we take off these mirrors. There's an adapter on it so that it cannot be destroyed by any machinery. This is a typical picture how it is built. You see the wire mesh here, here's the rock outside, and then we spray this into the shotcrete, and here in this area we put in our adapter afterwards. This is then the finalized situation, this steel board in, and here's the adapter, which we can take off for construction. This is a typical strain unit which is brought into the shotcrete shell. So this is a DMS, as we call it, measures the strain in this area, and using this flow rate method for the calculation of the shotcrete, which I brought in my first lesson, is telling you epsilon is well known. So if I know the epsilon, I can back calculate the sigma. the stress. Brought into the shotgrid shell like this one, I mount it on the wire mesh and measure the strain inside the shotgrid. This picture we already saw, shotgrid testing in a very early stage. A very good idea came from Professor Roca from Hanover. He retired already. He had an idea some years before. He said, we would like to know if there is a crack in the shotgrid shell, but often we have the case that we put material in there to be able to go on with our machinery. So we put the material in, and his suggestion was to put in a pipe into this shotgrid shell, and then we pull through a so-called mouse, which is nothing else than a small bore. And if you can pull this small bore from this area to this area, then everything is intact. If you have a shearing off of your shotgrid shell, you cannot pull your mouse through, your bore through, because then you destroyed your shotgrid anywhere here. Yeah? So a good, very easy, very cheap methodology to check if this shotgrid shell is still working. Extensometer, just to say, is a fixed instrument deep inside of the rock. No touching of this pipe anywhere. And you measure, with this point outside here, you measure the movement of this point in here. So if you put in an extensometer for 25 meters, you are able to say, what is my movement in 25 meters distance of the underground structure. And of course, we would like to see what forces are on the board, so we use a load plate to be able to say something about that. And then by having these extensometers available, you can find out structures behind the tunnel, because your movement is so different due to this extensometer results, so that you can start to make such sketches as shown here. Next point is, we did a lot of measurement now. We would like to interpret it. Now I can put the results on diagrams in a different way. The easiest way is to use displacement history diagrams. What does it mean? I put the displacement on one axis and the days on the other. So after each day, I have a displacement. And what is the result? I put the date on this axis, I put the settlement or the deformation on this axis, and if I have normal behavior, I expect to get such a curve. And if something is not going right, it goes this direction. And from this curve, I immediately see if something is going wrong. Same for the bench construction. Of course, if I put out the bench, I expect that we get some settlements. But if it's not going right, there's an instability problem. I will see that on this curve. Now, an important thing, which is very important for the surveyors. And there's fully automated nowadays, because we had big problems with the results of these curves when it started. Let's assume the face is here. Here is our tunnel face. Then, of course, after opening the tunnel, we have to mark out. We cannot measure something. Again, the rock is not waiting with its deformation. Then the surveyor, hopefully, let's say we open the face at 3 in the morning. The surveyor sleeps. And the surveyor comes after breakfast, so around 9 or 10. Then, of course, a lot of deformation has gone until he makes his zero measurement. So it is very, very essential that the zero measurement is done as soon as possible. And nowadays, if he measures, we get the time, the date and the time on the paper, on the file. And we also get from the construction company, when did they open the face? So we can immediately say, okay, you opened your face at, let's say, 2:30 in the morning. The surveyor was here 3 in the morning, marking was done, 3 in the morning. He did the zero measurement, and then we start. And then we can get this curve. Still, it must be clear that this is not the measurement which you can compare with the design calculation. Because in the design calculation, you started from 0 here, which is starting far in front of the face. Because if you open a face, you have movements inside the face, which nowadays can be measured, but you can imagine the area is quite soft and it moves in. And because of moving in the rock material, you also have already some settlements behind. Yeah? So you have, as we call it, a pre-deformation in front of the face. And there are calculation methodologies now available. If you have this curve, what was then this curve? How did we get that? We put in pipes far in front of the face and measured what is the deformation in front of the face. Quite clear to measure, but I need some measurement in front of the face. The best results for that were done at the Gotthard base tunnel. By Heinz Erber, you might remember. They put, I don't know, 100-meter long board measurements into the face to see what is going on in front of the face if I come closer. It's a kind of extensometer which was used there. But this is a very essential information because the surveyors sometimes came late. And then we had, let's say, the 0 measurement here, and then a measurement. You can imagine if this is the 0 measurement point and we get a very low deformation, we, as an engineer, would think, yeah, everything is okay. But we didn't realize that he measured much too late. So what can be calculated nowadays is if I have these results available, I can do a back calculation in front. In 20 meters in front of the face, we had already the starting point of the deformation. The other point is there is very much difference on the velocity, how fast are you going. In the beginning of the deformations, as you see, we have the displacement here and the time after the 0 measurement here. You see, if I drive slower, if I do, let's say, 2 meters a day, I will get a more comfortable line than if I do 5 meters a day. And if I would do 10 meters a day, I would fall down this direction. But at the end, and this is important information, I have the same, if I have the same geology, I have the same result at the end. That's why we like to plot this information in another way nowadays. And we plot the information depending on the phase distance. Because there the velocity is not playing a role anymore. I plot this information depending on how far is my phase away, and then I get for the same for the different velocities the same curves. What else is possible? Trend lines, contour plots, lining utilization. I would like to show you some examples. As we have this shotgrid model now developed, and we know or we measure the deformation of these shotgrid shells, we can immediately say the utilization, I mean how far are we away from the strength of the shotgrid. Everywhere where it's blue lined, it says, okay, absolutely no problem. And where it gets a red color, we know, okay, we are on the upper limit. We are close to a crack for the shotgrid shell. This is a sidewall gallery construction in the middle of Vienna, Leinzer Tunnel, where this was done first. Is now, I would say, state of the art to be used. Deflection curves. The problem is with these mirrors, you get a lot of information. You have cross sections, let's say every 20 meters, and you have 5 mirrors in one cross section. You get a lot of information on your table every day. That's why we developed an interpretation paper which makes it a little bit easier. You have the tunnel longitudinal section shown here, and you connect measurement results at the same time measured. It's a little bit hard to understand for the moment, it's an own lesson normally. However, if the areas between the lines do not change, everything is stable. This is the outcome of this result. So if the geology is homogeneous, you will get the same area in between. If a fault zone is coming in front, your deflection line reacts. You get more distance, you see, between these points, which means your area opens up. And you can see that quite easily. Something is getting bigger, there must be a fault zone in front. This is how you check also your geological engineer, because he doesn't have this information, just the geotechnical engineer has it, and you can prove with him, okay, does he say a fault zone is coming? Here you can already see that. And if you are going through, it's getting even bigger. Just one step further to that, you can also combine in a certain distance from the face a so-called trend line, and as long as these areas in between these lines are the same, you have a horizontal trend line. If the area grows up a little bit, your trend line goes down. And if your trend line goes down, it's a signal I have to react. Just this said. What else can we do? We can put on a cross-section the deformation of the mirrors. You see, the deformation of the mirror says all the cross-section goes inside. That's what we assume. We open an underground structure. What we assume is a convergence of all the parts. That's what we see, convergence from all the sides. What we see here is interesting. You see the point of the top heading is going down. Okay, nothing very spectacular. The point 5 moves in, point 4 moves in, so we have convergence. Yes, that's what we expected. But then, after a certain moment, this point moves outside and this point moves outside. So it changes from a convergence to move outside, but the roof still goes down, which means the shotcrete shell goes down and the legs go out. And this is not a very comfortable situation for a shotcrete shell, because there's not so much reinforcement in to take a moment. So it happens that it goes this way. And this can be seen very easily by such a sketch. Or you see that this movement, point number 5, is coming in, while number 4 is keeping constant. What does it mean? A fault zone must be there, because the stress goes in here. If you have a fault zone going close to the underground structure, the whole stress must go through this area, and this moves your shotcrete shell in. So we can learn something out of this, also shown in this sketch. On the vice versa situation, you see very high deformation because of this fault zone coming close. What we recommend is to bring the information of the geologist on the same picture than the geotechnical information. You see, we did that here, just put the points a little bit outside to see everything. We put the geological outcome, what the geologist did, together with this geotechnical engineer. And the guideline says they have to sit together and explain why this happened. And then normally at 5 in the afternoon, I don't know what the Swiss regulation is, but in Austria at 5, we meet with the construction site supervision and the site manager and tell everything is okay, what normally they want to hear, of course. But sometimes we have to say something is going wrong, we have to change. This situation, what I showed you before, this moves outside, this moves outside, and this goes down, led to a collapse. Of course, after the collapse, it's always easy to say what was the reason. If you are under stress, of course, it's not so easy to react, and you have a hardliner on the other side and say, no, we don't change anything, then it's not so easy to change something. Settlements on the surface can be measured. Of course, we have a calculation. Normally, this was around this geometry on the surface. Tunnel had to be built through. From the calculation, we know what is the distance where we expect absolutely no settlements. And then we put the points on the left and right-hand side and get such curves from time to time. When the tunnel goes through, we get this curve. Nowadays, we make colored plots, so we can see where the tunnel moves, colored plots from the surface. So you can watch from the surface, okay, where is the tunnel moving ahead, because you see the settlement developing. Phase monitoring nowadays is developed without any reflectors, because the problem in earlier times was we always needed a reflector for that. So nowadays we put a theodolite on the top point here and watch at the tunnel phase in a 5 seconds distance, or time distance, so we immediately see what's going on. Of course, we do that in very sensible regions. If you have a house on here, this is a construction site in Vienna, nothing must happen. Would be the same situation. You build a subway here in Buenos Aires, then you have to take care what is going on with the houses, of course. So the theodolite is hanging here, and we watch every 5 seconds. Okay, stable, stable, stable. Newest development on that point is a laser scanner who is able to make a full screen of the short pitch shell. You get out such figures, tunnel meter on the one hand side, circumference line. So we could place a tunnel scanner here and make within 3 seconds a photo of all of you, and we have the coordinates of everybody of you, because it turns around at, I think, 10,000 times in a second. So this rotates with a really high speed, and then we take a photo with all the coordinates. And this is what we use in the tunnel for the moment. Inclinometers to see if an open pit, for example, moves. We put in a plastic pipe and measure with an electronic device if something moves in this pipe. And of course, if I make an open pit and I have an inclinometer behind and I dig out my open pit, something in the wall could move. And I can see that from such a measurement device. It's a pipe where we put in our electronic device meter per meter to see if the pipe gets any inclination. Yeah, all of that works, I would say, if we have an organization chart behind where everybody takes his responsibility. The responsibility, of course, first is at the client. The client doesn't have so much stuff that he can do everything himself. I don't know how it is organized here, but normally they take some colleagues from different parts. Of course, the construction company. In earlier times, this chart was shown, the construction company should build it, and it was a kind of secretary shown in this chart, and we changed that because we had a lot of complaints. The construction company has to get, and this was the requirement of them, has to get the same information than the client-side supervision. Who prepares the information? As I said, the geological documentation staff, the geotechnical engineer, and of course somebody who does the monitoring, who does the analysis. Flowing together this information to the geotechnical engineer, he's the one who does the interpretation, but very essential, he has no right to decide something, because he is not responsible for the contract. He is a kind of advisor. He should advise the construction company and the site supervision, I would do this and that. Yeah, it's like a medical doctor. He cannot say, you must do the operation. No, it's up to you. He can say, I would take this medicine. If you take it, leave it or take it. Yeah, but it's the same situation here. The geotechnical engineers can say, I'm coming from the design. I know what's going on. I would recommend this and that. The construction company can say, okay, I have it in my contract, I do it, or I make a fine claim out of it. The client's site supervision can say, no, it's too expensive, or yes, I like it. Whatever, the decision makers are normally these two. And what I mentioned, we would like to get rid of the lawyers. We install on normally every construction site a so-called tunneling expert. And he's of course not a lawyer. He says, from my point of view, he is invited all the design meetings, which normally take place every 6 weeks, depending on the size of the construction site. But he is invited just to listen, does say nothing. But he knows all the history. And then, normally, if they do not come to a conclusion, to the same conclusion, I mean, then they ask the tunneling expert, and normally they follow the tunneling expert before going to judge. If they don't follow, of course, everybody is open to go to catch up a lawyer. But we learned it gets more and more complicated because the lawyers on each side then make a kind of acquisition out of that. Yes, that's it. What I wanted to tell you about monitoring, and we have some minutes left if there's some question open. I went through quite quickly in some points, but I'm happy to get some questions from your side. Thanks for the attention.